Hello, it's Scott Manley here. Today, I woke up at 4 a.m. because SpaceX was scheduled to perform their most ambitious Starship Super Heavy launch yet. Honestly, every single one of their launches has been more ambitious than the last, but this one seemed particularly audacious. They were going to attempt something that had never been done before. Sure, SpaceX had successfully landed hundreds of boosters on drone ships, but today, they were hoping to pluck one right out of the air using the launch tower. Mechazilla was set to reach out with open arms and carefully grab the booster using two very small pins on the side. Were they going to be able to pull this off? That's why I was up at 4 a.m. As many of you already know, they did succeed. Not only did they manage to land the super heavy booster on the tower, but they also successfully descended a Starship through the atmosphere with pinpoint accuracy, landing that too. This achievement is a marvelous testimony to the power of engineering and human ingenuity. We all knew that this was technically possible, but there were so many things that could have gone wrong, so many small factors in the engineering and physics. It's one thing to take something that works on paper and actualize it into reality. I demonstrated this in Kerbal Space Program many years ago, but I didn't have to worry about budgets, risks to human life, or government paperwork. Plus, I had the ability to play the video backward. This was going to be the fifth flight of the combined Starship Super Heavy stack. To summarize how we got here, the first flight got off to a rocky start, literally. A rock tornado cast debris all over the area, a number of engines failed, and there was a fire in the rear. They lost control of the booster, which eventually spun out of control. Neither of the stages separated, the flight termination system fired, but it didn't destroy the rocket until a minute or so later. Flight 2 solved the rock tornado problem with a giant showerhead, a water deluge system that protected the surface and, moreover, seemed to help protect all the engines. We had 100% success, at least early on in the flight. The flip stage separation procedure was replaced by a more conventional hot staging system, requiring a hot staging shield on top of the main booster. This resulted in a successful and spectacular stage separation sequence, which got even more spectacular moments later when the booster exploded. Starship continued downrange but eventually ran out of oxygen, leading to flight termination. Flight 3 pushed the envelope even further. After hot staging, both stages completed their intended burns, with Starship heading across the oceans and the booster coming back into the Gulf of Mexico. The booster descended straight down through the atmosphere, but it was lost. Starship performed a number of tests in orbit but lost attitude control and was destroyed on re-entry. For Flight 4, the big change was that they were no longer going to use the hot staging ring, which had added extra mass to the booster. After stage separation and boost back, they dropped the hot staging ring into the Gulf, while the booster continued down under good control, demonstrating a descent through the clouds at multiple times the speed of sound before lighting all its engines, decelerating quickly, and achieving a soft landing in the Gulf of Mexico. We have these images because a boy there had a camera. This also demonstrated the precision needed to move on to the next step in their test plan. Starship's descent was even more spectacular because it began to disintegrate. We started to see holes being burned through those control fins, but miraculously, despite sustaining damage, it managed to maintain control and land safely in the ocean. For Flight 5, Starship's task was to land precisely where expected. I was concerned that the launch might be delayed. They pushed it to 25 minutes into their 30-minute launch window, but it went off on schedule. The early part of the flight has become well understood. The launch took off without throwing rocks everywhere and ascended through Max Q at a beautiful sunrise. This launch was probably the most photogenic yet, with deep red colors from the low sun in the sky making the plume easier to see. As it got higher, we could see a dark shadow being cast across the Earth by the low-flying rocket. The real action starts at staging, where a lot of work with the rocket's plumbing is necessary to shut down engines, start others, and restart various engines. We've seen things go wrong during this phase before, but everything seemed to work fine this time. One of the things I really liked about this particular flight was that we got to see it from the ground, and the onboard camera from Starship was able to pick out the booster in the distance. As Starship maneuvered to its new attitude, you could see a bright light in the distance that was the booster firing its engines. The pin sticking out on the booster is what will be caught by the tower's capture mechanism. It performed most of the boost back on 13 engines, shutting down 10 of those engines near the end and leaving 3 for the final, precise correction for entry. Then, it shut down those 3 engines, and again, you could see the puffs of gas as it did that. Now, the booster is on its way home, and this is a view from Starship showing one of the new cameras that provides a view of the booster. It was lobbed onto a trajectory bringing it back just off the coast of Boca Chica, maxing out at 96 kilometers, technically not over the Kármán line according to Blue Origin but over it according to Virgin Galactic, so you can decide if it went to space or not. The point is, this booster is big, heavy, and full of propellant. For it to reach the landing site, it must perform a glide using its grid fins to steer itself. If it fails, it should just land harmlessly in the water. They also had to explicitly send a command to the booster, conducting a system checkout before enabling the mission. You'll notice that in the last few seconds, it has aligned itself to the entry attitude. The puffs of gas initially seen are now getting pulled along by the atmosphere, and we're at 100,000 feet, where the atmosphere is thick enough to. Certainly. Here's the text you provided, restructured into a coherent paragraph. The rocket is currently ascending with balloons holding it up, moving at a speed that is beginning to decrease as the booster experiences drag. This descent is much faster than that of a Falcon 9 booster. As we switch to a ground camera, we can see the booster leaving a trail, but interestingly, the bottom of the booster appears hot. You might think this is due to the rocket engines, but they have actually been shut down for a few minutes. Upon closer inspection, it's the shield around the engines that is hot, resulting from atmospheric heating inside the engine skirt. As it approaches the ground, it lights up 13 engines to decelerate, ensuring a safe landing. For finer control, it then switches back to 3 engines for those last-minute adjustments as it nears the tower, maneuvering between the giant chopsticks of Mechazilla. The arms of Mechazilla carefully close around the booster, successfully catching it, much to the crowd's excitement, reminiscent of a star batter being caught out in a baseball game. Rewinding a bit, you might notice debris being shed from the bottom of one of the chains, with a section cut out. Additionally, it's fascinating to observe how the booster actively maneuvers during its final descent. Many observers noted it appeared wobbly, but this was a planned maneuver designed with safety in mind, ensuring that if it were to fail, it would land clear of the tower and avoid causing damage. Only when the booster is certain of its trajectory does it translate toward the tower and begin to slow down, executing a side step at the last minute to prevent any potential damage. In a captivating display, the capture angle reveals the pins descending toward shock-absorbing rails, which absorb stress during landing. This design choice effectively distributes forces throughout the vehicle, potentially saving weight. Despite our awareness of this design gain, uncertainty about its feasibility lingered. Now, as we ponder the future, questions arise about the repeatability of this process. We also observe a vent on the side releasing methane, and due to airflow dynamics, the flames appear to rise against the flow before catching at the bottom and racing upward. This purging of the fuel system is crucial to prevent any explosive buildup. With the booster caught successfully, several processes will ensue to ensure its safety and recovery. Meanwhile, the Starship ascended to a suborbital trajectory at orbital speed, though it would not complete a full revolution. Its performance was adequate for space, reaching a maximum altitude of about 22 kilometers before descending. However, it did not have a flawless heat shield. Several tiles were damaged, particularly on the front wing. Some tiles were replaced with test hardware, while others were removed to gauge the vehicle's response. The heat shield had undergone redesigns, incorporating an ablative layer for thermal protection in case of missing tiles. Reflections of clouds can be seen in the polished stainless steel tanks during re-entry, where atmospheric conditions affect heat exposure. In the thin upper atmosphere, peak temperatures occur despite a lack of significant heat until descending into thicker air, where dynamic pressure peaks, resulting in the vehicle experiencing various heating regimes. Throughout this process, Starship must maintain the correct attitude, with the stainless steel shield facing the primary heating source. RCS thrusters fire intermittently, and as it dives deeper, the rear fins actively adjust to maintain stability. Aiming for precision, the design intends to recover Starship without landing legs, using an equivalent device to pluck it from the air. There are 4 cameras monitoring the descent, including one mounted on a fin. As the heat intensifies, the surfaces begin to change color, potentially due to steel heating or plasma reflections. Sparks indicate material shedding from the shield, an expected part of the development process. One forward fin shows signs of heating, raising concerns about whether tiles are missing or if hot gases are penetrating through the shielding. Forward fins struggle with sealing due to their attachment to a curved surface, leading to potential pressure and temperature variations. The images reveal the state of the fins, with rear fins appearing stable, while the right forward fin shows signs of failure. Despite these challenges, the vehicle maintains control and descends to a stable altitude, albeit with damaged fins. The Starship, now below 45 kilometers and slowing to less than 10,000 kilometers per hour, experiences a reduction in light from the plasma as it descends. The vessel employs a belly flop maneuver for a high drag orientation, which allows it to descend slowly, minimizing the engine burn needed for landing. As engines ignite, the reflections on the stainless steel surface are captivating. The intention is to land at a slight angle to recover something for later analysis. However, the booster ultimately falls over in the ocean, signaling the end of this phase, but a nearby buoy captures the aftermath, revealing a mushroom cloud of propellant. While the Starship's end was violent, remnants remain afloat, allowing for further analysis of the heat shield's performance. This journey serves as a testament to effective engineering, showcasing that despite significant control surface damage, the vehicle managed a soft landing and hit the target. Both the booster catch and the Starship descent demonstrate impressive successes in guidance software, though challenges with the heat shield remain. As SpaceX prepares for future missions, the potential for rapid progress is promising, allowing for the possibility of another launch without extensive changes to their flight profile.